Should I? Hi, my name is Kangwook. Today I'm going to talk about how we can speed up distributed machine learning using codes. This is a co-work with Ramtin Pedarsani, Dimitri, Kanan, and we are all from UC Berkeley. So the motivation is coming from the common architecture of distributed machine learning platforms. So we are looking at two possible problems we are seeing. One problem is called the straggler problem. So straggler problem is as follows. So you have a job that is distributed across multiple workers. But even though you give the same amount of jobs to these workers, some of them is, for some random reasons, they are slower than the others. So how can you deal with this kind of stragglers? That's the straggler problem. And even in the experimental case, we actually saw that 5% of the workers are slower than the others in our test platform. Another problem we are seeing in the current platform is you have to shuffle this training data between the workers, between the iterations, but the communication overhead of that operation is too much. So we want to minimize the communication overhead of that. So it is clear that if you do shuffle data between iterations, you can converge much faster. But in practice, due to this communication overhead, people are not shuffling data. So how can you reduce this communication overhead? That's the goal of the second part. So we have two parts. Let me first go over the first part of the poster. So the first title of the first part is Coded Computation for Straggler Mitigation. So our assumption is a computing time of each worker is shifted exponential random variables, and they are IID across the workers. With that assumption, what we can show is if you use coded computation, your runtime is going to be 1 over n, while if you're not using coded computation, if you're using uncoded computation, or if you're using replication, your average runtime is going to be log n over n. So we can improve the runtime by a factor of log n using the coded computation. So the idea is very simple. So you can see the ideas through this example. So let's say you want to do matrix multiplication where A is huge, so you divide A into 3 workers. Each worker is going to compute small matrix multiplication, and the master node is going to collect 3 different results. But the problem is you have to wait for all of 3 workers to be done. But that will determine the computation time, which is the maximum of 3 random variables. In the second case, where we are using coded computation, you divide the matrix into 2 blocks instead of 3. And the last worker is going to compute A1 plus A2 times X, so that each of the computing is slightly larger than the previous case, but you don't have to wait for all of 3. You can just wait until 2 guys are done, then you can still get the result. So in the test platforms, we have seen that 40% gain in the average runtime and more than 50% gain reduction in tail latency. So I can go to the next session. So the idea here is if you have a broadcasting channel, you can exploit the coding opportunity. The reason is in the iteration T, worker 1 wants to update their lows so that you can work on fresh samples in the next iteration. But the rows that you want to download is actually stored at some other nodes. So using that, exploring that fact, master node can mix the rows of the data, and using the broadcast channel, you can reduce the communication overhead. But the problem is in current data center, we don't have broadcasting channel, but you can actually use the networking trick so that you can implement pseudo broadcasting nature even with the unicast channel. So in our platform, we have tested this, and you can show that instead of having perfect broadcast gain, which is n, we can achieve n over log n, which is a pseudo broadcasting gain. Okay, so those are the 2 ideas we propose for speeding up machine learning using code. If you want to know more about details, you can check out the full version on archive. Thanks.